Welcome everyone. These are some of the topics that we'll try to cover in this chapter, atoms and molecules. So first up, let's try to define the laws of chemical combination. These laws of chemical combination were formulated by Lavoisier and Joseph I. Proust after thorough examination. And in this law of chemical combination, there are two laws: law of conservation of mass and law of constant proportion. So what is law of conservation of mass? By the term itself, we can say that anything matter is conserved, that matters or mass is conserved for that matter. Now, in the event of any reaction, any chemical combination, the mass of the components does not vary, it does not change, it remains the same even after combining with each other. Suppose if you dissolve sugar in water, salt in water, when you mix it, then you see that the salt or the sugar has vanished. But once you evaporate the water, then you get back the sugar or salt. So which shows that the salt doesn't vanish. That means it's conserved, it doesn't change. The combination is the same even though we try and mix together. Suppose even if you're preparing tea or coffee or any beverage or lemonade, even if you mix those different things, still then you can get back the original components once you distill it or filter it out. That means the mass is conserved, it doesn't change. And then law of constant proportion states that when chemicals combine, they do so in fixed proportion, constant proportion, meaning water, suppose for example water is H2O, that means 2 parts of hydrogen and 1 part of oxygen, they combine to give us water. Even if it's the ocean, the water in the ocean or a drop of water, it will still have this H2O. That means it is fixed, we cannot change it. Once you alter it, it is a different chemical. Suppose if it is H2 and we increase the oxygen by 1, then it's hydrogen peroxide, a different chemical, which is a bleaching agent. But this one, it's potable, we can drink it, it's safe. But this one, it's very corrosive. Now let's turn our focus to John Dalton, an English scientist in the 18th century. He discovered the atomic theory. He formulated the atomic theory. Here in this theory, he stated that all matter is composed of very tiny particles called atoms. Suppose, imagine you break a substance, suppose a cube of sugar. You go on breaking it, you magnify, and then you notice that the crushed sugar cube will appear bigger if you magnify it. You still break it down again, where will you end up? So Dalton proposed that you'll end up with something indivisible, and that he termed as atom, from the Greek word adomia, which means indivisible. But these days, through recent discoveries, we know that atoms can also be further divided into subatomic particles. But for the purpose of this video, we'll stick to that it is an indivisible entity. Or atoms is the smallest entity that can participate in a chemical reaction. That's what it is. Now again, in Dalton's atomic theory, he found out that atoms cannot be created or destroyed in a chemical reaction. That means it's conservation of mass. We cannot create or destroy mass. Atoms of a given element are identical in their mass and their chemical properties. Of a given element, of a particular an atom of a particular element, they'll be identical. They'll be same. Atoms of different elements have different masses and chemical properties. And then atoms combine in the ratio of small whole numbers to form compounds. That is the law of constant proportion. Even if we try to alter it, it'll still end up with suppose waters. For water, it'll still it will still end up in H2O, or for that matter, hydrogen peroxide. It will still end up as hydrogen peroxide when we try and mix it. No, even if we add 50 liters of hydrogen and 50 liters of oxygen, we'll still end up with H2O when we get water or hydrogen peroxide. So I hope you understand what I'm trying to picture here. Now let's turn our focus to an atom. Now from Dalton's atomic theory, we know that atom is an indivisible entity, a very small microscopic particle. So, but how big is an atom? Certainly we cannot see an atom, even with the help of an electron microscope, which has very high magnification. We still cannot see an atom. It's very difficult to see an atom because it's microscopic, and then we may get a picture of the electron distribution within the atom, but we cannot for sure picture what we cannot see or look what an atom is, or we cannot picture an atom exactly as it is. If we think about the size of a suppose say a daily object, a cup, it's big, we can hold it. But when we think about an ant, it's of the order of 10 raised to the power -2 meters. That means 0.01 meters, which is quite small, but still we can see it. What about a grain of sand? A grain of sand is of the order of 10 raised to the power -4 meters. So we have 0.3 meter. Still smaller, but still we can see it. But what about a molecule of water? A molecule of water is 10 raised to the power -9 meters, or 1 nanometer. Okay, we can also write it as 1 nanometer, which is very, very small. We cannot see. But for example, hydrogen atom, it's this much big, or we can say it's 1 angstrom. Very small. So you can now think or have a picture of how small an atom is. Now, before scientists, before the advent of the Mendeleev's periodic table, the symbols, atomic symbols, were different. Suppose for hydrogen, they use this symbol. For sulfur, like this. For lead, it was this. For phosphorus, this, and so on. Sorry, this one is for platina or platinum. But there are 100+ elements in the periodic table. So if we try to give symbols, a symbol to each of the element, then it'll be difficult to remember also. So for that, scientists came up with a shorthand. Suppose for hydrogen, we simply use the letter H, and this is for hydrogen. Suppose for carbon, we use C. For oxygen, we use O, capital O. But there are some elements which still we use the trivial names or the old names that were given to them. Suppose for silver, we silver we use AG or argentum, or for gold we use AU aurum. These are Latin words that has been given or assigned to those metals or atoms. So those are the symbols in the periodic table. You can look up at the periodic table and try and identify the symbol so that you'll be at ease in learning chemistry as well as physics. Now let's talk something on atomic mass. Since atoms are also a form of matter, it should have mass, because we know that matter is anything that occupies space and has mass. So let's try to define atomic mass. We know that the atoms are really small, of the order of 10 raised to the power negative 10 meters, but it still exists, so it should have mass. So how can we determine the mass of an atom? Now scientists were trying to define or trying to find out how to measure an atomic mass, because for measuring something, for example liquid, our frame of reference or how we measure is in terms of liters, milliliters, and so on. And for length we have meters, kilometers, or feet, and so on. But what about atom mass? We know that it's in terms of kilograms, grams, and milligrams, and so on. But how will we measure something which is very small? Now they figured out that carbon 12 is an carbon we know has 3 isotopes, C12, 13, and 14. So this carbon 12, if you break it into 12 parts, that means 1 out of 12 is equal to 1 atomic mass unit, or which is very close to the weight of one hydrogen atom. So that is how they formulated the standard unit for measuring or obtaining the atomic mass. So we simply say these days, it's 1 unit. For example, carbon 12, since 12 is the mass number, so it will have 12 units. For the next isotope it will have 13 units, and so on. For oxygen we know it's 16 units. For hydrogen it has 1 unit, atomic mass unit, and so on. That's how we determine atomic mass. Okay, now let's shift our attention to a molecule. Now we know that atoms are very small, and they are the smallest entity that can participate in a chemical reaction, or when it comes to combining with different elements. Atoms can participate. Atoms are the smallest entity that can participate in chemical combination. Now, but atoms, most of the elements, they cannot. Most of the atoms of different elements, they don't exist independently. So what they do, they aggregate, or they combine with other molecules, or with other atoms, or of the same atoms. They combine together, and they exist in that state, and when they combine, they give us molecules. So for example, hydrogen, we know that the symbol is H, but it doesn't exist this way. Hydrogen molecule, it can exist as H2. For example, oxygen also, it cannot exist as O, so it exists as O2. It can exist as ozone also, O3, but the freely occurring, that the air that we breathe, or the gas that sustains us, this oxygen, O2. So two atoms of hydrogen, they combine and give us H2. 1 plus 1 gives us 2H. Oxygen, similarly, we get O2, and so on. Therefore, these are called as the molecules, and molecules also, they combine to give us compounds, different compounds. So when this hydrogen and oxygen, they combine, they give us water. So this is a molecule of water, or compound. Water is a compound because it has hydrogen and oxygen in it. That is how molecules exist. And this shows that except for some metals, it is difficult to find atoms naturally to exist independently. It is difficult for them to exist independently. Hence, they combine with each other to give us molecules. Okay, let's turn our attention to ions. Now, what are ions? Now, we know that atoms are neutrally charged when found in nature, but once an atom carries a charge, either a positive or a negative charge, then we call them as ions. Suppose, for example, hydrogen we write as H, but if it is H plus, then it's a hydrogen ion. Or suppose oxygen we write O, but if it carries a charge, then it's an oxygen ion. Now, these positive and negative charges are really important. This positive charge indicates that hydrogen has lost one electron, because here it's only positive, that means one is there. But in oxygen, we see two negatives. That means oxygen has two extra electrons apart from its own electrons. For example, sodium, we write this is sodium ion. Or chlorine, we write chlorine ion as this way, one negative. That means it has one electron more. This sodium has lost one electron. And even for example, best example, beryllium. Suppose beryllium can have 2 plus also. We can have more charges also for different atoms depending on their electronic configuration. But now, when we have positive ions, then we call them as cations. And when we have negative charge, then we call them as anions. Now, to remember this, you think about this plus in cations. This plus suggests that the atom will carry a plus charge, and so on. Now we know that an atom can carry a charge. So suppose this hydrogen, oxygen, chlorine, and all are gases, so they come under monoatomic non-metallic ions. But suppose for beryllium or sodium, these are metals, so they are metallic ions. We can have polyatomic ions also. Suppose polyatomic means more than two atoms, different atoms that carries charges. Suppose, for example, ammonium ion, H4 plus. So see, it has nitrogen and hydrogen, so it's polyatomic. Or for the phosphorus, PO4, three negative, phosphorus and oxygen. So this is also an example of polyatomic ion, because it has two different atoms. Now, how or why does they have charges, or how does the charge come about? So we can explain this by something called valency. Of course, it's only in the next chapter, but we'll try to analyze what is valency in order to understand why these ions carry charges. Now, when we talk about valency, it means the ability of an atom to donate or accept electron depending on the number of atoms it has. So therefore, suppose, for example, a hydrogen atom, it has only one electron. Therefore, Now, electrons in an atom are filled are filled with are filled into different orbits inside the atom of different elements, and we follow one rule, twice n squared rule. This is one rule which we follow for filling up electrons. So suppose n is the number of orbitals. Suppose for hydrogen, we know that hydrogen has only one orbital. So for hydrogen, 2 into 1 squared is equal to 2. So the first orbital can carry a maximum of 2 electrons. For second orbital, it can carry a maximum of 8 electrons, and so on. Now, once you go on filling the electrons in an atom, the electrons, suppose in the second orbital, if the electrons are fully filled, that means one atom, suppose for example neon has 10 electrons. So 10 electrons means in neon atom, the first orbital will have 2 electrons and the second orbital will have 8 electrons. That means it is fully filled. 2, 4, 6, 8. It is fully filled. That means its valency is 0. That means it cannot accept or donate any electrons. But if suppose for example an atom, carbon has 6 electrons. So in the first orbital it will have 2 electrons and 2 electrons in the first orbital, and the remaining 4 will go into the second electron. So that means carbon has still 4 vacancy left to be fully filled. So its valency is 4, and so on. Now I think you get a picture of what the valency is. Now, how to write chemical formulae? So for writing chemical formulas, we need to know, or we need to have an idea of the valency of a particular atom. Suppose, for example, we know that when hydrogen and oxygen they combine, we get water. But what about the valency? Now, the valency of hydrogen, as I've already told you, it's 1, and oxygen, it's 2. Forget about the charges. So for writing water, you just cross multiply, then we get O is 1, H is 2, so H2O. That is how we write water, the formula of water, by knowing the valency of each of the atoms. How oxygen has 2 valency. Now oxygen, we know its atomic number is 8, which means it has 8 electrons. So if we fill the orbitals by twice n squared method, the first orbital will have 2 electrons and the second orbital will have 6 electrons. So it has 2 vacancy left. That's why its valency is 2, and so on. Suppose for common salt, sodium chloride, we know that sodium we denote by Na and chlorine we denote by Cl. So when we look at the valency of chlorine, it's -1, and sodium it's +1. So I just cross multiply and we get sodium chloride. We don't need to write the ones. If it is more than 1, we have to address it or write it down to make or to generate the chemical formula. Suppose sodium carbonate, we know that sodium is +1, and carbonate, CO3, has -2 charges. So if we cross multiply, we get sodium carbonate. And so by knowing the valency of each of the atoms, or for that matter each particular ions, then we can easily generate the chemical formula. Now the last topic, molecular mass and mole concept. What is a molecular mass? Molecular mass simply means the total weight or the total mass of a particular compound or molecule. Now, for instance, let's say water, H2O. Now, I've already mentioned that hydrogen, its atomic mass unit is 1, but it has 2 hydrogen in this molecule, so we multiply it with 2. And then oxygen has 16 atomic mass units, so you multiply it with 1 because it has only one atom. So if we add it, then our molecular mass of water is 18 units, or 18 atomic mass units. For example, we can take another example, like suppose hydrogen peroxide. So 1 into 2 plus 16 into 2, which gives us 32 plus 4, 32 plus 2, it's 34 units. That is how we calculate the molecular mass of different molecules or compounds. Even compounds we can calculate. For example, ammonia and H3. So we know that nitrogen atomic mass is 14. So 14 units, 14 into 1 plus 1 into 3, which gives us 17 units. That is how we calculate molecular mass. Now, when it comes to mole concept, suppose for example water. 1 liter of water, 1 liter of water, 1 liter of hydrogen peroxide, and 1 liter of ammonia. All of these 3 compounds will have different weights if it is just 1 liter. So how to equate it or equalize it? It is given by this mole concept. Now, what is mole? Mole means, what is mole? Mole is simply a number, a frame of reference for calculating or for equating molecular masses of different compounds. So mole. Now I've told you it's just a number, and the number is a huge one, 6.02 into 10 raised to the power 23 entities or particles or atoms. Each mole, suppose 1 mole of hydrogen will have this much particles, 1 mole of water will also have this much atoms or molecules in it. That is what mole is all about. It's like the currency, the exchange for equating different atoms or compounds while we do chemical reactions. So that is all about mole. Suppose that is all about this chapter. Like for example, let's say H2 plus oxygen, half of oxygen gives us water. So here we don't have any number on the left side, so this means 1 mole of water. 1 mole of water. That means it will have 6.02 into 10 raised to the power 23 molecules of water. But suppose if we increase it to H2O plus 2 into half of O2, then we get 2H2O. So since we have a number on the left side, that means 2 moles of water. So it'll have 2 into 6.02 into 10 raised to the power 23 particles or molecules of water in this. And so that is the concept of mole, which is a really important concept for chemistry.